Welcome students again into the 12th science chemistry class. Today we mainly have to learn about the packaging efficiency, but there are few things which we already learned, but these are very important for solving the numericals. So let us learn again the coordination number in close packed structures. Now there are the three close packed structures. We already this is learned in the last lecture, that is the simple cubic structure, that is SC, and the second one is the hexagonal cubic packed structure HCP, and third one is the face centered cubic structure, or it is also called as the that is cubic packed structure. Now these three are there, that is the close packed structures. So we have to learn here what is the coordination number in these close packed structures. The first one is in the simple cubic, that is SC. It is also called as SCC, simple cubic crystal, or only SC, that is the simple cubic. So in the simple cubic crystal structure, we already know that the coordination number is 6, because in its own layer there are the 4 spheres touches the given sphere, and one is above and one is the below. So 6 is the coordination number. So in simple cubic crystal structure, each sphere is surrounded by 6 neighboring spheres, that are 4 in its own layer, 1 above and 1 below. Hence the coordination number of any sphere in the simple cubic crystal is 6. Remember that. So in simple cubic crystal, the coordination number of any sphere is 6. Now in both HCP, hexagonal close packed, and CCP, cubic close packed, or it is also called as the face centered cubic structure. So in that structure, each sphere is surrounded by 12 neighboring spheres. So the coordination number is 12, that are 6 in its own layer, 3 above layer, and 3 are in the below layer. So in both SCP or CCP, SCP and CCP or FCC, the structures in that structures, each sphere is surrounded by 12 neighboring spheres, 6 in its own layer, 3 above and 3 below. Hence the coordination number of any sphere in hexagonal close pack or cubic close pack, or it is also called as the face centered cubic structure, the coordination number is always 12. So these are about the coordination number. Now let us, we have to learn how the voids are there, and how the number of voids are calculated in the numericals. Now we have to only learn the voids of the hexagonal close pack or face centered cubic cell. The simple cubic, in the simple cubic unit cell, we have not calculated the voids. Now in this, the number of voids per atom in HCP or CCP, or it is also called as the FCC. So there are two types of voids. We already learned that. That is the tetrahedral voids and the octahedral voids. Now there are two types of voids in HCP and CCP or FCC structure, the tetrahedral and octahedral voids. Now there are two tetrahedral voids per atom or associated with each atom. That means if there is the one atom in the unit cell, then there are two tetrahedral voids in that unit cell. Remember that. That means if the SCP has only one atom or FCC has only one atom in that unit cell, then there are the two tetrahedral voids. But we know that in the FCC, there are the how many? That is the 4 atoms. So 4 multiplied by 2, that is the 8 tetrahedral voids are present in FCC. Now, and how many octahedral voids? So remember, per atom there are the 2 tetrahedral voids. And the number of octahedral voids is always half that of the tetrahedral voids. That means if the tetrahedral voids are 2, so that is there is definitely the octahedral void is 1. So half of the tetrahedral void per atom there are octahedral voids. So thus there is 1 octahedral void per atom in the FCC or HCP cubic closed structures. So in this way we can calculate the number of voids according to the presence of atoms in that unit cell. Now let us learn the main topic, that is the packaging efficiency of the cubic closed structure. Now this packaging efficiency determines that the structure is more compact, there are the spheres which are more close to each other or not, and how many that is the empty space present in that crystal lattice. Now let us learn the packaging efficiency in the closed packed structures. Now pay attention on blackboard. Packing efficiency. Now the magnitude of the packing efficiency measures how tightly or compactly the particles are packed in the crystal, packed together in the crystal structure. So packing efficiency is very important, whose magnitude tells us about the measure of how tightly the particles are packed in the crystal structure. Now packing efficiency is defined as, it is the fraction or percentage. Packing efficiency is the fraction or percentage of the total space occupied by the particles in the crystal structure. So packing efficiency is nothing but it is the percentage of the space occupied by that particles in the crystal. So from this formula we can calculate the packing efficiency in the crystal lattice. Now packing efficiency is equal to volume occupied by particles in the unit cell. How many particles are there and what is the volume of that particles in the unit cell divided by total volume of the unit cell. Because in the unit cell there is some voids also. So the total volume of unit cell is not the volume of the total particles. So packing efficiency is equal to volume occupied by the particles in the unit cell divided by total volume of the unit cell into 100. Now this is the formula to calculate the packing efficiency. So to calculate packing efficiency in simple cubic or in HCP or in FCC, first we have to calculate the volume occupied by the particles in that unit cell. Then we have to calculate the total volume of the unit cell and just multiply by 100. Then you get the packing efficiency. Now let us first calculate the packing efficiency of the crystal in the simple cubic unit cell. So how it is calculated? So the packing efficiency of the metal crystal in the simple cubic unit cell or lattice is obtained by the following steps. Now first we have to calculate the volume of the particle in that unit cell, one particle. So to calculate we know that we consider the particle as the spheres and we know the volume of the spheres from the 10th standard. What is that? 4 by 3 pi r cube. Now 4 by 3 pi r cube is the volume of the sphere, that is volume of the particle. But what is the radius of that particle? That gives the volume of that particle. So this is the face view of the simple cubic unit cell. So this is the figure of the face of simple cubic unit cell. Any one face. Now we know that in the simple cubic unit cell, the particles are touches with each other in the edge. So if we join the centers of that particles, then we obtain the edge length of the simple cubic unit cell. Let us the edge length is small a, and this small a is obtained by joining the radius of the adjacent spheres. So this is the radius of the sphere, and 2r is equal to a, that is the edge length of the unit cell. So to calculate the radius r of the sphere from the figure, suppose a is the edge length of the unit cell, then r is the radius of the atom. So the edge length of the unit cell is equal to a, that is equal to 2r. So if we have to calculate the r, that is the radius of the sphere, then as a is equal to 2r, therefore r is equal to a divided by 2. Now in the second step, we have to calculate the volume of the sphere, that is the volume of the one particle. Now volume of sphere is equal to 4 by 3 pi r cube, which is the volume of the particle in the unit cell. On substituting the value of r in this equation, we obtain the volume of one particle as 4 by 3 pi, and here r is substituted as a divided by 2 and its cube. So if we calculate this, 4 by 3 pi a cube divided by 2's cube means 2 into 2 into 2, then what? This 4 and this 4 get cancelled, and there is a pi a cube divided by 3 multiplied by 2, that is the 6. So the volume of the one particle is equal to pi a cube divided by 6. Now always the volume of one particle in simple cubic unit cell is calculated by the formula pi a cube divided by 6. And if we substitute these values in that is the volume of the one particle, we have to calculate here, and how many particle in that crystal structure. We know that in the simple crystal structure, the volume, there is only one particle. So the volume of one particle is nothing but the volume occupied by the particle in the unit cell, and the total volume of the unit cell is calculated by multiplying the length into breadth into height, and all is similar, a. So a cube is the volume, total volume of the unit cell, and just multiply by 100, we obtain here the packing efficiency. Let us calculate the packing efficiency in the simple cubic unit cell. Now see students on blackboard. In step 3rd, we have to calculate the total volume of the particle. Now as in the simple cubic unit cell, there is only one particle. So the total volume of the particle is the volume of one particle. So because the simple cubic unit cell contain only one particle, volume occupied by the particle is in the unit cell is equal to nothing but the volume of one particle. And what is the volume of one particle? Pi into a cube divided by 6. Just we calculate that. Now let us calculate the packing efficiency of simple cubic unit cell. We know the formula of the packing efficiency. Packing efficiency is equal to volume occupied by the particle in the unit cell divided by total volume of the unit cell into 100. We know the total volume of the unit cell is a cube. as the edge length is A. So A cube is the total volume of the unit cell. So volume of one particle is pi A cube divided by 6 divided by volume of the unit cell A cube into 100. If we calculate it, now this pi A cube divided by 6 and this is the multiply by 1 divided by A cube here. Now this A cube get cancelled here and this is the 100 again multiply by it. So what is remaining? The remaining is only 100 into pi divided by 6. So this is the 100 into pi divided by 6. In this way. Now the value of the pi, we know that 3.142 is the value of the pi. So if we substitute the value of pi here, so 100 into 3.142 divided by 6. And if we calculate this, the value comes 52.36%. Now this is the packing efficiency of the simple cubic unit cell. That means in the total volume of the simple cubic unit cell, the particles occupied the volume 52.36%. Then how many empty space is present in that simple cubic unit cell? If we subtract this, that is the 52.36 from the 100, suppose the total volume, the total percentage is 100 of the volume in the unit cell of simple cubic unit cell. Then only by subtracting the volume of the particles from the 100, we obtain the volume of the empty space. So this is nearly equal to, that is 47.64. So in simple cubic unit cell, total space occupied by the particle is 52.36% and empty space, that is the void, is 47.64%. Now nearly half of the voids are there. So in simple cubic unit cell, the packing efficiency is not much and therefore the particles are somewhat loosely held. Now we have to calculate again that is the packing efficiency of the HCP and also that is the FCC. Then we determine which unit cell is more compactly packed by the particles, and that will we calculate in the next lecture. Now if student you understand this packing efficiency very well in this video, how the packing efficiency of the simple cubic unit cell we calculated here and what is the formula, and from that how we can calculate the volume of the empty space also. If you understand this very well, you like, subscribe and share this video to the other students also, and tell them to like and subscribe so that this video becomes efficient and more, that is the students can be benefited by this, that is the topic, and they also can solve their entrance examination questions and numericals very successfully. Thank you for watching this video.